For 5 years, the artificial intelligence industry followed a singular path: add more parameters to larger compute clusters for guaranteed gains. Today, that linear relationship between compute and intelligence has broken. The primary mechanism for scaling has stalled because developers are depleting the foundational fuel of the internet age. High-quality, unique human text is a finite resource. When that massive reservoir of blogs, books, and code repositories dries up, the established method for expanding intelligence fails. OpenAI researcher Lillian Wang recently confirmed the severity of this shift, reporting that the industry has officially entered the data-limited region. In this environment, billions of dollars in hardware and trillions of parameters no longer produce a corresponding leap in reasoning capability. The models are getting larger, but they are not getting smarter. This chart tracks global unique text data availability against frontier model parameter counts. We see a hard crossover in 2026 where data demand surpasses human supply. Above this limit, the parameter line pushes into the red, yielding severely diminishing returns. Because pure compute brute force has reached a physical boundary, the industry must pivot. The focus is shifting away from pre-training expansion and moving entirely towards system-level inference engineering. The billions poured into massive data centers were justified by 2 scaling laws, Kaplan in 2020 and Chinchilla in 2022. Both provided the mathematical confidence for the recent investment boom. The 2020 Kaplan law predicted a massive advantage for raw model size, but this conclusion was built on a critical experimental error that overestimated how large models actually needed to be. Kaplan's team omitted the embedding parameters from their calculations. While insignificant in small models, removing this variable corrupted the logarithmic math, causing their predictions to skew wildly off target as models scaled toward 1 trillion parameters. The competing Chinchilla law was thought to be the correction, until researcher Tamay Besiroglu identified an error in their loss function. By averaging loss values instead of summing them, the minimizer triggered premature termination, massively overestimating their scaling trajectory. The reality of the math is captured by Lovelace's 2026 research on the overfitting penalty. When a massive model is forced to train on repeated, non-unique data, it incurs an exponential decay in performance. Training on repeated data actively degrades reasoning. Consequently, capital is migrating away from the pre-training phase and moving towards solving the bottlenecks in the post-training inference layer. When we talk about inference, the process of an AI actually generating an answer, we hit a physical wall called autoregressive generation. To produce one word, the system pushes the model's entire memory state through a narrow pipeline, then pulls it back. Generation is constrained by data movement, not processor speed. The compute unit sits idle while the system chokes shuttling data. To bypass this hardware limit, engineers introduced a software hack known as speculative decoding. Instead of calculating one word at a time, a smaller, cheaper draft model guesses multiple tokens at once. The massive target model then verifies the entire string in a single efficient batch pass. Early attempts used serial draft models, guessing words one by one. The latency scaled linearly with every drafted word, defeating the speed advantage. Switching to parallel draft models created cross-mode collisions. Because the model guesses multiple words independently, it loses grammatical context, often generating nonsensical hallucinations. If the target model rejects these guesses, the massive GPU wastes cycle time verifying useless text, leaving the core memory bottleneck unresolved. The breakthrough for the draft failure rate came from the Chinese AI lab DeepSeek through a semi-autoregressive framework called DSpark. DSpark uses a dual architecture approach. First, the draft head handles the heavy lifting, processing a large batch of tokens simultaneously. Then, a serial Markov head intercepts the output, rearranging any conflicting pair to repair cross-mode collisions before reaching the main model. Because the Markov head is incredibly shallow, this localized correction happens with almost zero latency overhead. These corrections increase the average length of accepted tokens by up to 31% over baseline draft models. But the algorithmic fix is only half the equation. DeepSeek paired it with a system-level innovation, confidence-scheduled verification. previous systems verified fixed-length blocks of text blindly. Regardless of server traffic, they spent the same compute cycles checking the drafts. Confidence-scheduled verification links directly to the physical hardware. When the GPU is busy, the scheduler truncates the verification block to save compute. When the server is idle, it extends the verification to maximum length. By combining the Markov head with dynamic scheduling, DeepSeek achieved a 400% increase in high concurrency throughput, all without requiring engineers to retrain the base model. DeepSeek proved that clever software can squeeze extreme efficiency out of existing hardware, but algorithms eventually hit a physical ceiling, forcing the industry to redesign the silicon itself. The global AI infrastructure was built on a compromise. Tech giants relied on generic GPUs that were architected to train models, not to run them in production. This chart shows the architecture of the NVIDIA Blackwell platform. While powerful, this training-focused design is inherently misaligned with the specific demands of LLM API serving. Forcing sequential inference through hardware built for parallel training creates massive power waste and delays data movement. The physical solution is the Jalapeno processor, a custom AI inference chip developed jointly by OpenAI and Broadcom. A generic GPU relies on complex, tangled pathways between memory and compute. Jalapeno uses a blank slate design, streamlining data movement, balancing compute cores with Tomahawk high-speed network nodes to eliminate the physical memory latency that chokes text generation. Aided by AI code generation, the hardware moved from initial design to physical tape-out in just 9 months. Escaping the memory bottleneck requires absolute vertical integration. The silicon must be co-designed from the ground up, tailored to the specific algorithms and models it will execute. By late 2026, the industry had mapped a completely vertically integrated technology stack. The physical base is the Jalapeno custom silicon. The DSpark algorithm locks in directly above. Finally, the GPT 5.6 Sol foundational model caps the top. Coupling these layers solves immediate latency constraints, driving inference costs down to a fraction of previous levels. Technologist Dwarkesh Patel notes that ultra-cheap inference serves a purpose beyond faster query times. It provides the overhead required for models to continue learning after they are deployed. By replacing pre-release parameter expansion with continual learning, developers can bypass the physical constraints of the data wall. On-policy self-distillation, or OPSD, provides the mathematical framework for this ongoing evolution. OPSD captures real-world friction. Every user interaction, failed logic attempt, and human correction is captured and immediately distilled back into the model's weights. This feedback loop takes complex, sparse tasks like coding or legal analysis and refines the core model in real time. This approach was impossible prior to 2026. It requires near-infinite, zero-cost inference to constantly run background simulations and internally dream new skills to prevent catastrophic forgetting. Because this learning happens dynamically in live production, the models evolve into highly specialized assets. Competitors cannot simply copy the results. This dynamic specialization is why advanced inference stacks are now guarded by federal export controls and targeted by adversarial distillation attacks. The capability itself is a strategic resource. The industry has moved past the method of blindly pouring data into generic hardware. The focus is now on engineering surgically precise, closed-loop inference engines. The competitive moat in AI has shifted. It is no longer defined by raw pre-training data, but by a vertically integrated inference stack capable of evolving continuously in the wild.